Okay, good morning. Some of you have emailed me you'd like to talk about your exam, but you can't come during my normal office hours. I'm trying to get to those emails as quickly as I can. If I'm not able to meet as soon as you might prefer, the teaching assistants all have copies of the exam key, and they are happy to talk about that with you when they're available. So if by some chance I tell you I can't get to you immediately and you need an answer immediately, consider talking to the TAs. Otherwise, I'm happy to meet with you. It just may take me a minute. Of course, if you come during regular office hours, which are Monday through Friday at 1 p.m., no need for an appointment, I'll be there. All right, so we have been talking about alcohol chemistry. The theme is turning the OH into a good leaving group. We have strongly acidic conditions, which go through carbocation intermediates, and we're afraid of rearrangement being a possibility. So last time we introduced a few new reagents that can do substitution chemistry without a carbocation intermediate. This was SOCl2 and PBr3. And then paratoluene sulfonyl chloride, TSCl. And just at the end of class last time, I introduced POCL, the reagent that can do elimination chemistry without going through a carbocation intermediate. So I will show you this mechanism. Again, along the way, it's going to be the same sort of story. There's an unfamiliar reagent. And then intermediate where the oxygen, the OH, is turned into a good leaving group. You're going to have questions about why doesn't it do substitution chemistry, and I'm going to have to answer, I don't know, only the reaction works. So we can go ahead and use it. I'll show you the mechanism, but as with SOCl2 and PBr3 and toluene sulfonyl chloride, the mechanism may be useful to you in terms of remembering what happens, but I'm not going to ask you to push the arrows. You will, however, need to know, for example, with POCL, that it's an E2 mechanism, excuse me, with no carbocation intermediate. So, POCl3, I don't know what's going on with the voice. Excuse me, that's really obnoxious, I'm sorry. POCl3 looks like this. As before, oxygen-phosphorus bonds are really strong, so there is a driving force for oxygen to attack phosphorus and to kick off one of the chloros. That's sort of an SN2 step on its own, but at the phosphorus. And then you generate this intermediate. This should look pretty familiar. It should look very similar to the intermediate that's in the SOCl2 reaction and in the PBr3 reaction. Now, Cl minus sort of left from phosphorus. It does not come in and do substitution chemistry here, and why that is, I don't know. Pyridine is added as a base, presumably to do the elimination reaction. Probably, if you think about this as a good leaving group, then we're looking for protons that are beta to that leaving group. However, it looks like you need 2 molecules of pyridine in order to do this reaction, because the first one is going to remove the proton on that positively charged oxygen. That just makes sense in terms of the pKa of a positively charged oxygen with a proton on it relative to the pKa of the conjugate acid of your base, this pyridinium ion. So once you've done that, again, we're focusing in on protons that are beta to the leaving group that can get anti to the leaving group. We've deliberately chosen an example here where stereochemistry is not going to be an issue. This proton here that is orange, by rotation around this carbon-carbon bond, it can get anti to the leaving group. And when it does so, no matter how we arrange things, If we remove this beta proton, we've got a new double bond here, and that's the orange product. And you see how in this deliberately chosen example, there is no E and Z isomers here. It's just one stereo. It's just one product. There's no possibility for stereo isomerism when one of the carbons in the double bond is attached to two of the same thing. So that's why I'm not worried about drawing this in a way such that the proton appears anti to the leaving group. I just know that it can be, and that when it is, it leads to this product. So removing the orange beta proton with another molecule of pyridine. So you'd need at least 2 for every molecule of starting material you have. Does the E2 reaction step. Of course, if instead we removed the blue beta proton, that would lead to the blue product above, and I'll just show you that mechanistic step. Again, we'll have pyridine act as the base, leaving group leaves, and that gives us our products with no rearrangement. Same standard E2 rules apply. The more substituted alkene is going to be the major product, and so on. Okay, questions about that? All right, so probably there's some details in this series of reactions, these new reagents that we've talked about last time and this time. Probably there's some details there you're just going to have to memorize. Nothing is going to save you on the exam from looking at POCl3 and saying, I forgot what that does. Like, it really can't help you there if you can't remember it. So take some time and do whatever works for you to memorize stuff. And I've given you some recommendations on, a flashcard strategy if that might be helpful. All right. In the last bit of chapter 9, we turn to a unique class of molecules called epoxides. We're not going to learn how to make epoxides for a while, but we're going to learn what you can do with epoxides now. And we'll talk mostly about the chemistry, and then if we have a little bit of time at the end, we'll talk about Gorilla Glue and epoxy resin and how that works. So an epoxide is a 3-membered ring in which one of the atoms is an oxygen. It's an ether. It's a cyclic ether, 3-membered ring ether. And it may help to draw in hydrogens that are implied but not shown. Let's see, we're not going to worry about epoxide nomenclature or how to talk about epoxides. But one of the epoxides have unique reactivity that other ethers do not. We've started to be used to the idea that OH minus and by extension OR minus are terrible leaving groups. Nevertheless, in the epoxide, we're going to see chemistry occur that you might otherwise expect wouldn't occur. That is, epoxides are good electrophiles, and we're going to see nucleophiles attack and open up epoxides in an SN2-like fashion. And the leaving group here is a negatively charged oxygen. Now, I've deliberately chosen an epoxide that where the 2 carbons attached to the oxygen, we'll call them A and B, are not stereocenters. So you can't actually tell, or from this example, you can't really tell or appreciate the stereochemical issues that occur, but opening of epoxides happens through backside attack with inversion of configuration, just like you would expect for an SN2 reaction. Now, why do you suppose it's okay for this OR minus to leave? for the epoxide. Anything that might explain that when we've never really seen that happen before? Go ahead.
Is there like some weird torsional strain type stuff going on with it being a three-member ring?
Yeah, great. You've got ring strain associated with the three-membered ring. In a triangle, the internal angles need to be around 60 degrees. I don't know, actually, the epoxide doesn't have to be an equilateral triangle, but we won't worry about that. In any case, that's a lot more tight of an angle than you expect for an sp3 hybridized carbon. So yeah, there's a lot of ring strain, and when you open it up, you relieve that ring strain. So to some extent, relief of strain pays for the poor leaving group. All right, so we're going to be okay with epoxides opening up with nucleophiles to give you a negatively charged oxygen as an intermediate. Of course, that negatively charged oxygen is not what you isolate when you open up an epoxide in the lab. Often when you do these reactions, there is what I will call aqueous workup. That's not going to make any sense to you until you've actually done it in the 353 lab that some of you have to take. When you're done with the reaction, you have to isolate your desired product from any of the undesired byproducts of the reaction. And one of the most common ways to do this is if you're doing your reaction in an organic solvent, you add water, and sometimes there are things in the water you add to help to clean up the reaction. And the details there aren't particularly important for our purposes now. Sometimes you add a little bit of sodium bicarbonate to soak up whatever acid reagent you have used. Other times you add sodium chloride to help pull water out of the organic phase. In any case, aqueous workup basically means you add water at the end of the reaction. You shake things up, and then you pull off, because the water and the organic solvents don't mix, you can easily separate them. And usually what's left behind in the organic layer, or in the organic solvent after you've removed the water, is your desired product and maybe some other things, and you have to do some other purification. In any case, that step of adding the water allows you to protonate any negatively charged oxygens that have pKa's such that they can remove protons from water. So aqueous workup means that at some point I add water, and then just through simple acid-base chemistry, simply pKa-based, I protonate the negatively charged oxygen. Now, so my product is going to have my nucleophile on carbon A and my OH group on carbon B. This pattern of 1,2 nucleophile and OH on adjacent carbons, that 1,2 substitution pattern, is characteristic for opening up of an epoxide. In the near future, you're going to be doing synthesis problems where somebody's going to show you a molecule and ask you, how do I synthesize it? And being able to recognize certain structural patterns in a product is a key to helping you figure out how you could have made that product in the first place. And this is one of those patterns. If you have what was a nucleophile and is one bond away or one carbon away from an OH group, you could have made that by opening up an epoxide with a nucleophile. And that's something that you'll need to practice and that you can get through some experience by doing some synthesis problems at in the end of the chapter and in the study guides and practice exams. All right, so any questions about epoxide opening? Yeah. What happens if it's unsymmetrical? We will talk about that. So the question is, what if A and B are different? Then you've got what are called regioselectivity issues. Regioselectivity refers to selectivity between two different constitutional isomers. I'll give you some examples of that in a little bit. Other questions? Yeah.
Does it matter which carbon you attack in this scenario?
Yeah, does it matter which carbon you attack? And that's basically the issue. And the answer is yes, not here, because carbons A and B are identical. But if we added some stuff to carbon B such that they were different, yes, if you attacked at A, you would get a different product from if you attacked at B. And we will be able to do one or the other depending on reaction conditions. That's the regioselectivity issue. Good. Others? Okay. Before we get to the issue of regioselectivity, I want to talk about the stereochemical issues associated with epoxide opening. All of that is basically summarized in this backside attack with inversion of configuration, but it's hard because it involves visualizing molecules in 3D. So you're going to need some practice on this. There is a problem on the next exam that if you don't get this down really well, you haven't got a prayer. I mean, you can pray, and it will help, but it probably won't give you the right answer. So, yes, it's true. The Holy Spirit can bring all things to your remembrance, but you got to put it in your brain in the first place before the Holy Ghost can do that. So let's work on that with epoxide opening and stereochemical issues. Yes, praying for the Holy Ghost to help when you haven't studied is like praying for God to bless the ice cream to nourish and strengthen you. Is that? Anyway, random thoughts. So, here we go. Let's follow the stereochemical outcome of epoxide opening. So, I'm going to deliberately choose our examples at this stage such that there are no issues with whether you attack A or B. In the epoxides that I draw for the next few minutes, A and B are going to be identical. But we will still be able to see what the stereochemical outcome of the reaction is. So, here is an epoxide. Methyl groups are there. And we'll put hydrogens here. There are a couple of ways you can choose to draw epoxides, a couple of ways you can choose to show epoxide opening. We'll use this one, but as time goes on, if there's other alternatives, I'll show them to you. Just for fun, is this epoxide chiral? No. Does it have stereocenters? Four different things there, four different things there. Yes, it has stereocenters, but it is not chiral because of a plane of symmetry there. What's on the left is a reflection of what's on the right. This is what I mean when I say carbon A and carbon B are identical. This is an example of a meso epoxide. It is meso because it has stereocenters, but it is not chiral. So, having established that carbons A and B are identical, I'm only going to draw a mechanism where I show you attacking carbon A. All right, because A and B are identical. Well, maybe we'll do both. Let's actually choose what the nucleophile is at this point. Let's choose OH minus. And let's show OH minus attacking carbon A to open up the epoxide. That's going to generate, and I'm going to skip the aqueous workup if it's okay, because we know that that OH group is going to, that negatively charged oxygen that left is going to pick up a proton when we add water at the end of the reaction. I'm going to skip that step in the mechanism, and we're just going to go all the way to the final product. For fun, I'm going to still label carbons A and B. Carbon B didn't get inversion of configuration because carbon B isn't the one that was attacked. The nucleophile came in from the backside, and so that OH group on carbon A came in opposite to where the leaving group was leaving. The methyl group, which was pointed towards the bottom of the page but coming out towards us, is now, this is how you show inversion of configuration, is now going to be still coming out towards us but angled up towards the top of the page. And the proton, which was also angled towards the bottom of the page but down away from us into the page, is still going to be down away from us into the page, but now angled up towards the top. Okay? This is one way you can show inversion of configuration. Yes? Is there a reason I drew 2 arrows? Yes, you need 2 arrows. One, to show formation of the bond between, oh, here, sorry. I drew 2 arrows because I am skipping this intermediate, whoa, that's an eraser. I am skipping this intermediate and this protonation step. Yeah. Okay. All right, questions about that? So my product has an OH on both carbons. One question we could ask at this point is this product chiral? That can be difficult to see in the way that we've drawn it. The key to determining whether it's chiral would be, one method would be to draw its mirror image and see whether they're the same thing. Another thing you can do, especially when you're in a situation, I don't know if you've noticed, but on carbon A, I have an OH, a methyl group, and a proton. On carbon B, I have an OH, a methyl group, and a proton. So that's a classic situation where there's the potential for some symmetry that would make this molecule not chiral. So in order to check for that, I'm simply going to rotate around the bond between A and B to bring the OHs eclipsed with each other. Carbon A stays exactly the same as it was. Because I'm grabbing that OH group and bringing it back down and around so that it's pointing to the bottom of the page, that's going to bring my proton forward as a wedge and my methyl group backwards as a dash. And when I do that, it becomes a little bit clearer that there's no plane of symmetry here. The product is chiral. Now, that should make you worried because there is no chirality out of nothing in organic chemistry. And my starting material was not chiral. If I'm going to make a chiral product, I have to have made the other enantiomer. Where does that other enantiomer come from? Go ahead. Yeah, let's attack carbon B. Carbon A and B are identical, right? So they have to attack at A or B has to happen at the same rate. This is the product we get from attack at A. I'm not going to draw the mechanism for attack at B, but I will draw the product, and that would look like this. This is carbon A, this is B. And then if I were to rotate around carbon-carbon bonds, the bond between A and B, you should be able to see as we're drawing this that those two products are mirror images of each other, but are not the same thing. And the word we use for that is enantiomers. All right. Now, a key skill here is not only being able to think forwards, as we have done, starting with the meso-epoxide, following the stereochemical outcome of the SN2 reaction out until we get to this product, but also an important skill would be to be, if you were given the stereochemistry of the product, to be able to say what the starting material must have been. Okay? So we'll do that in just a second. I want to point out, remember how I said that with epoxides, when you open them up, you have this 1-2 substitution pattern with your nucleophile and your OH group. What we've just done here has been to use the OH minus hydroxide as your nucleophile. Of course, the leaving group of the epoxide ends up, after aqueous workup, being an OH group as well. So when you open up an epoxide with OH minus, your product is a 1,2 diol, alcohols on carbons 1 and 2. So in a synthesis problem, if you see a 1,2 diol, you need to be thinking, okay, I could have made that by opening up an epoxide with OH minus. All right. So let's do a related problem backwards. I'm going to draw a 1,2 diol product, and then we're going to think about what the starting material would have been. Okay, so there is a 1,2 diol product. Note that this product is actually not chiral. It's a meso compound. It's got stereocenters, but nevertheless, it is not chiral because of the plane of symmetry that shows you that carbons A and B are equal to each other. So let me show you how to think backwards. You've got to remember and know that opening of, okay, hold on. First, you recognize that this is a 1,2 diol, and right away you're thinking, I could have made that through epoxide opening. But you know that epoxide opening happens via SN2 with inversion of configuration. So the first thing you do before trying to think backwards too much is you want to draw the molecule as it would have appeared immediately after backside attack. So I'm going to arrange things so that the OH on carbon A and the OH on carbon B are pointing in opposite directions, because that's what we did before to show that backside attack had happened. So see, I'm rotating around the bond between A and B so that the OHs on A and B are in opposite directions. When I do that, the methyl group on carbon B is still a wedge, but the methyl group on carbon A should now be a dash and pointing in this direction. Do you see that? And now here's the key step. What was the starting material? The starting material is an epoxide where, and at this stage, as I'm looking at these OHs, I probably don't know which one was the oxygen from my epoxide and which one came from the hydroxide. It's okay not to know. You don't have to, it doesn't matter. Pick one of them. I picked the one on top. All right, I picked the OH on carbon B to be the one that was in the epoxide. If the OH on carbon B, and I'll just use highlighting to indicate, we'll use, green for the leaving group. And then we'll use blue for the hydroxide. Now all that's left is for me to sort out the stereochemistry. If the green oxygen becomes the leaving group that's the OH group on carbon B, that means my nucleophile attacked carbon A, right? That means stereochemistry on carbon B didn't change, which means my methyl group is still a wedge on carbon B. How about on carbon A, where there should be a methyl group on carbon A? Should it be a dash or a wedge, and where should it be pointed? That's confusing, right? When you do inversion of configuration from this angle, basically in the plane of the page. You show inversion of configuration by having this dash that's pointed towards the bottom of the page now be pointed towards the top of the page. Okay? So yeah, that's the starting material that we would get, that we would use to get the meso epoxide. And I'll leave it to you to show that if you attacked at carbon B instead of A, that you would get this product. But if you rotate around carbon-carbon bonds, you can see that both of those are the same meso compound. Okay, I'm a little bit worried about that because some of you were not predicting correctly what inversion of configuration would look like there. This is a 3D visualization problem. Questions about that? I'll ask one for you. Dr. Price? Yes? I thought that inversion of configuration went like this, that when a nucleophile attacks, what is a wedge becomes a dash. Yes, that's true from a certain point of view, but notice, yeah, thanks Obi-Wan. What I told you is true from a certain point of view. Big cop-out. It's true but notice the difference between the situation below and the situation above. Here, the leaving group was a wedge, and it was pointed towards the top of the page. We show inversion of configuration by showing after the nucleophile attacks and the leaving group leaves, and that's a terrible leaving group, so we'll just go leaving group. The nucleophile is now a wedge oriented towards the bottom of the page. When your leaving group is in the plane of the page, this is how you show inversion of configuration. With a model set, you can convince yourself, let's just, maybe this will be useful, maybe it won't. An equivalent way to draw an epoxide is to have the bonds to the oxygen be oriented towards the top. I'm sorry, the bonds to the oxygen be wedges, and the methyl groups there be in the plane of the page. And in this case, if a nucleophile attacked, the product would be, a correct way to draw the product would be this. You should convince yourself that this stereochemical configuration here is the same as this one. So there are a couple of different ways that you can show epoxide opening. You should choose whichever one makes sense to you. But, and again, if you're feeling confused on this issue, take a moment, build a model set, and convince yourself that what I've drawn here, let's let this, sorry, I don't need to be general, we can be specific. Convince yourself that what I've drawn here is exactly the same configuration as, let's see, this product here where we attacked at A. All right. Questions about the epoxide opening? 1, 2 dials? Yes?
So you showed with the green OH group and the blue OH group, if we treat it the opposite way as the green one is the one that joins instead of the blue one, it seems like the initial reaction would actually have the opposite stereochemical configuration,
Okay, right. So if you were thinking backwards and you chose the green OH to be the nucleophile and the blue OH to have been the epoxide oxygen, then yes, you probably would have suggested that this was the starting material. That would be correct too.
Okay, so there'd be also the starting material.
That's right. Notice actually that this starting material is chiral, and this one is chiral as well. They would both lead to, continue to use color the way you've suggested, both of those starting materials, these are enantiomers of each other, they're going to lead to the same meso product if you open them with OH minus. Yeah. Yeah, so you're absolutely right. This is not the only allowed starting material. This one would work too. Yep, good. Yes?
So basically, if you start with like a cis ring or like a meso compound, you end with two enantiomers, and if you start with a trans ring, you end with an achiral molecule.
Yeah, it's kind of beautiful the way that works. If you start with the meso epoxide and open it with OH minus, you end up with two enantiomers as products. But if you start with one or both of the enantiomers for the trans epoxide, you get a meso compound as your output. It's kind of weird the way that works. But this is a demonstration actually of a principle in organic chemistry called stereospecificity. And it refers to reactions that have mechanisms that only allow specific stereochemical outcomes. Notice, and you can tell when a reaction is stereospecific because if you change the stereochemistry of the starting material, the stereochemistry of the products must change as well. Notice the relationship between these two starting materials. The meso epoxide and this pair of enantiomers here, those are diastereomers of each other, right? Same is true of the products. The products from the meso epoxide, this pair of enantiomers, they are diastereomers of the product from opening of the other epoxide. Okay, so that seems simple enough, but I can guarantee you there are going to be times in your future where there's a product and you're going to have to know what the stereochemistry of the epoxide starting material was. It's going to get worse because we're actually also going to learn how to make the epoxide, and there's going to be some stereochemical issues there as well. So practice this as much as you can because that's going to be pretty important. Now, I told you we would get to the issue of epoxide regioselectivity. So let's do that. Regioselectivity in epoxide opening. This regioselectivity refers to selectivity among constitutional isomers. Another term for constitutional isomers is regioisomers. So I'm going to choose an epoxide here where the two carbons are different. And I'm going to draw this epoxide because I'm using a 6-membered ring. It's just easier to draw it this way. And you've got two options here. You've got option A, or you've got carbon A or carbon B, and carbon A and B are not identical. So the question is, if I use a nucleophile, am I going to get regioisomer, fine, we can call it regioisomer A, because you would get it from attack at A. And if that were the case, then the nucleophile is going to come in opposite. If we attacked at A, the nucleophile is going to come in opposite the leaving group. The new bond will be between the nucleophile and carbon A. The leaving group will have left, and stereochemistry at carbon B doesn't change. At carbon A, to show inversion of configuration from this perspective, the nucleophile is going to be a dash, and the methyl group, which used to be a dash, is now going to be a wedge. What I just showed you for epoxide opening is analogous to what I showed you up here from opening of an epoxide from this perspective. Okay? Option B is if the nucleophile attacks at carbon B, and if that happens, the OH from the epoxide is going to be a wedge on carbon A. The methyl group is still going to be a dash on carbon A, and on carbon B, the nucleophile should be here. And so the big question is, which one is it? And the answer is, it depends. That's your favorite answer. But it depends in a sensible and rational way. So we have two different methods for opening of epoxides. Method one is using a strong nucleophile, and generally we're thinking about things that are negatively charged. All right. And I guess I should add, we're using a strong nucleophile that's negatively charged, and the leaving group is a negatively charged oxygen. That's all we've done so far with opening of epoxides. We haven't considered any other options, and we will in just a minute. So let's say our nucleophile is, let's let our nucleophile be a negatively charged conjugate base of an alkyne. This is an acetylide ion. We've used that before in chapter 7 and 8 for SN2 chemistry. If we use a strong nucleophile under negatively charged conditions when OR minus is the leaving group, the biggest concern is sterics dominate. You've learned before that for SN2 reactions, they're fast at primary alkyl halides, are fast for primary leaving groups, they're slower for secondary, and they're not possible for tertiary. So you would expect there to be some preference for a strong negatively charged nucleophile to attack at the less substituted carbon. And indeed, that's what happens. If we redraw our epoxide starting material, here is your nucleophile. Nucleophile attacks less substituted carbon B. Leaving group leaves. I'm not going to show the negatively charged intermediate. I'll just show the product that you would get after aqueous workup. Okay. So epoxides open at the less substituted carbon when we're using a strong nucleophile under negatively charged conditions. Right. So what are our other options? Second option is that we open the epoxide under acidic conditions. We haven't considered that yet, but let's do that now. Let's take our same epoxide, but instead of using a strong negatively charged nucleophile, let's use an acid like HCl. We've done this before with alcohols, but what's going to happen here is very similar to what happens in the case of an alcohol. You add a strong acid, and the first thing that happens is we protonate the epoxide. Now, in the case before with alcohols, when we protonated the alcohol, we turned it into a good leaving group, right? We already said the epoxide is spring-loaded and poised to open because of the ring strain. When we protonate the epoxide, we turn it into an even better leaving group. What we observe when this happens as a product, what we isolate after we've protonated that epoxide is the following. It looks for all the world like the Cl- from HCl, has come in and attacked carbon A of the epoxide. That should make you uncomfortable. Why? Because it's OChem and it's still before 9 a.m. So what did you expect? But aside from that, why is that troublesome? Yeah. We did flip the stereo. We didn't flip the stereochemistry where? Okay, you were expecting chloro. Say that again? Oh, okay. But you're right, it does have to do with the stereochemistry. I told you something in chapter 7 and 8 about tertiary carbons. What was it? Go ahead. Told you SN2 doesn't happen at tertiary carbons. Nevertheless, I put the chloro as a wedge, and only as a wedge, seemingly indicating that this was backside attack at a tertiary carbon. That should be a problem, right? Well, so that tells you that something's going on here, and it's nuanced. If it were, so what you would have predicted, based on what you learned in chapter 7 and 8, is that the leaving group would leave, you would get a carbocation, and then the nucleophile would come in from above or below. Does that make sense? So I should have had another isomer with the chloro as a wedge and the methyl group as a dash. Nevertheless, this is the only product that is observed. All right, so that tells you actually that something a little bit more complicated is going on. To explain this, it's sometimes useful to think about reactions, especially like epoxide opening, as traversing a landscape. And there are two directions that there are two relevant directions in this reaction landscape. On the x-axis, we're going to have the nucleophile attacks. This is going to be one thing that's happening in the reaction. And then on the y-axis, we're going to have the leaving group leaves. This is something you've sort of thought about before. If a mechanism was SN2, the nucleophile attacks as the leaving group leaves. So this is the SN2 pathway. And there's some transition state here. This is the transition state for the SN2 reaction. Where on this plot is the SN1 mechanism? I would have to have the leaving group leave first to give me a carbocationic intermediate, right? And then I would have the nucleophile attack. All right, so in blue is our sort of SN2 path, and in orange is our SN1 path. And the transition state for the SN1 reaction is somewhere around here. Okay. And what you've learned so far is it's either one or the other, right? But there's actually a whole lot of real estate between those two. And reactions are often neither this pure SN2 pathway or this pure SN1 pathway. Sometimes they're intermediate between the two. So sometimes I'm going to show in purple a reaction pathway where the leaving group leaves a lot before the nucleophile starts to come in. Here's the transition state for our sort of weird intermediate reaction. Okay? And this transition state is one, as I said, where the leaving group is mostly gone, but the nucleophile is sort of still coming in. The transition state is much closer to a carbocation than the SN2 transition state is. And that's really what we're looking at for this reaction. What happens is that in the transition state for this reaction, which I'll draw for you next time, the leaving group is mostly gone, and the nucleophile is only partially coming in, but the leaving group isn't so far gone that the nucleophile can attack from either side. Okay? We'll say a little bit more about that next time, and then we'll move on to Chapter 10. Have a good Monday, and I'll see you Wednesday.